Okay, welcome back, everyone. Let's get straight into this deep dive. Today, we're looking at something, well, genuinely unexpected based on the source material you brought.
It really is. We're talking about connecting uh, pure mathematics, specifically derivatives from calculus.
Right, the rate of change stuff.
Exactly that.
Yeah.
Connecting that to a very real-world issue, heat stress in livestock.
And the sources get specific too, right? It's about animals working in post-harvest situations.
Precisely, post-harvest agricultural environments.
Yeah.
So quantifying that stress using mathematical models.
Okay, that's already interesting. Calculus and animal welfare. But then it gets even wilder
It does.
because the sources then pivot this whole discussion towards food science.
Yeah, and not just vaguely food science, but specifically volume of food packaging design. It seems like quite a leap.
It really does. So I guess our mission today is to trace that connection laid out in the sources.
That's it. How do we get from differentiation and integration, these abstract calculus tools, to modeling heat stress, and then somehow land on designing, the volume of a food container?
It's quite a journey. So let's start with step one, the derivatives and the heat stress. How do the sources say that works?
Well, the basic idea presented is that you can track physiological changes in the animals.
Hmm.
Think body temperature, maybe respiration rate, things like that.
Things that indicate stress.
Exactly. And the derivative is the mathematical tool that lets you measure the rate at which those things are changing over time, or maybe as the temperature climbs.
So not just if an animal is hot, but how quickly it's getting hotter or how fast its breathing is increasing.
Precisely. And knowing that rate, that speed of change, is apparently very important.
Why the rate, though? Why is that the critical part?
Because understanding how quickly stress is building up helps predict problems.
Hmm.
It informs when to intervene, how serious the situation might become. It's about managing the situation effectively for the animal's welfare and, well, for the farm's operation, too.
Right, okay. So you're capturing the dynamics of the stress. Makes sense.
You're getting a handle on how things are evolving.
Okay. Now for the big jump. How do we get from that stress modeling to food science and packaging volumes? What's the bridge the sources build?
This is where it gets, let's say, interpretive based on the material.
Right.
It connects that understanding of heat stress dynamics,
Hmm.
the stuff we got from the derivative models, to things you need to consider for packaging.
Okay.
How? Well, the sources mention integration being used in food science, especially for calculating volumes, like in packaging design.
So derivatives for the stress rate, integration for the package volume, two different tools.
Yes, but the implication in the material is that they're linked. The information from the heat stress modeling could influence the packaging decisions.
But what's the actual connection? Does stress change the, I don't know, the size of the animal product or something?
The material suggests it's more about the downstream effects. Factors impacting the animal, like heat stress, can affect the product itself. Maybe its quality, how quickly it might degrade, perhaps even its physical properties.
Ah, okay. So if the stress modeling predicts, say, a higher chance of quality issues.
Exactly. Then the packaging design, which involves calculating the right volume using integration, might need to account for that. Maybe you need a different type of packaging, or a different volume is optimal to maintain quality, given those upstream factors.
So the outputs of the farm level stress model using derivatives become inputs, or at least considerations, for the packaging design calculations using integration.
That seems to be the core idea presented. It's about how information flows and influences decisions across different stages, linked by these mathematical concepts.
That really is a surprising connection from animal physiology to package engineering.
It absolutely is.
Yeah.
And it shows how understanding a complex system, from the animal's well-being right through to the product on the shelf, can actually draw on the same fundamental math toolkit.
It connects fields you'd probably never think were related.
Mm-hmm.
So wrapping this up then, what's the main takeaway for you from digging into these sources?
I think the key thing is this clear, if unexpected chain the sources describe. You start with derivatives, modeling a real problem, heat stress, in livestock. Then that understanding, that data, feeds into considerations within food science, connecting eventually to integration used for practical things like calculating the volume of food packaging.
It really hammers home that calculus isn't just theoretical math problems. Derivatives, integration, these are tools with some really practical boots-on-the-ground applications.
Yeah, modeling complex things in places you wouldn't immediately look, like animal welfare, agricultural efficiency, and even packaging logistics.
It shows how math acts as this kind of universal language, doesn't it?
It really does bridge different scientific and technical domains.
Which kind of leaves a final thought for you, the listener.
Right. The next time you come across a mathematical idea, maybe something like a derivative, just pause for a second.
Consider where else it might be working sort of silently behind the scenes.
Yeah, modeling complex real-world situations in ways you haven't even imagined yet.